See if this actually works. Okay, so 1.8, if I punched it in right. That looks about right. Yep, this would be about 10 over 5, so good. 1.82 maybe. That's how long it takes to go around one time. That is what the period is. This is really part B that I'm doing here. Okay? All right, that's pretty fun to know. And then part A is we wanted to know omega in radians per second. Okay, so we can do it a lot of different ways. We know the frequency, so omega is 2 pi times the frequency. So we've got 2 pi radians, and then multiply it by the frequency. And again, let me write it, and then you'll see what I'm talking about. Here's the frequency, but the units look really ugly, don't they? This is radians, now this is revolutions per second. So really it's 2 pi radians per revolution. And then you end up with radians per second. So whatever that is. 1.1 pi maybe, or something like that, times 2. Let's just do it. Yep, 1.1 pi radians per second. And I just didn't want to multiply it out. You can multiply the pi out if you want to. I just did 2 times 0.55, and then still have the pi laying around there. Okay, good. Excellent. Any questions on this one? Let's look at one more question, and then if you have any questions, if not, we can call it a day after that. Let's just look at one more, though. So here we have 2 children are playing tetherball. That's the game where there's like a pole, and there's a rope, and a ball is on the end of it, and you gotta people are on the opposite sides. One person throws the ball this way, the other one can try to stop it and throw it back the other way. And I think the goal is to wrap it all the way around, if I remember right. Do they still have those anymore? Phased them out, okay. Wonder why that was a fun game. So anyway, that's the idea. You throw it around, the other person stops it, throws it this way. You try to get them not to catch it, because you want to wrap it all the way around. Okay, after a really good hit, the ball makes 3 revolutions in 2 seconds. And then we want to know what is the angular velocity, the angular speed, rather. So 3 revolutions in 2 seconds. We can get the regular frequency, right? The regular frequency is how many revolutions per second. That's what the regular frequency is. So really it's 3 divided by 2. That's what the regular frequency f is, right? How many revolutions you have per second. So once you get the regular frequency from this information, to get the angular speed, omega, it's 2 pi times that frequency. So it's really like what we did before. It's just you've got to solve for that f yourself. So take 3 divided by 2. That's the frequency. Multiply it by 2 pi to make it into an angular velocity. Okay? So without putting the numbers in, that's the way to do this one. Very good. So I think we have got a pretty good start, actually, for this chapter. Now tomorrow, if you're in Group A, we're doing that, it's called the human arm model. So here's my arm. Now the bicep muscle is actually connected really close to my elbow. So it's really connected close to the pivot point. It turns out if you want to lift something that weighs 10 newtons, the force that your muscle is actually putting in is more like 7 newtons. So you're actually providing a lot bigger force than what you're lifting. So you have a mechanical disadvantage the way that your bicep muscle is connected. So if you're trying to open up a door, so here's a door. So if I'm going to try to open the door, and here's the pivot point, and pretend it's already opened so it's not locked like this. You don't really try to open it here, right? It's really hard to do that because you have a really small lever arm. So you come over here, and you can open it with your pinky over here because you have a big lever arm. If you try to open it here with your pinky, there's no way. I would probably break my pinky. So by lever arm, I mean distance from the axis to over here. I get a really big torque, it's called, because I got a bigger lever arm here than I do over there. So your bicep muscle is connected close to the pivot point, so it's really gives you a mechanical disadvantage for that reason. Again, to lift 1 Newton, this muscle is doing something like 7 Newtons or something like that. So tomorrow, if you're in the lab, we'll have to have a little introduction about torque. Torque is what provides angular acceleration. That's how it's related to this chapter. So we'll actually measure this, not with your actual arm. We've got this model of your arm and a force probe, and we can measure different things. Okay, so that's something to look forward to this week and next week if you're in Group B. Okay, so that's all the new stuff for today. If you don't have any questions, you're free to go. If you do have questions, stick around. We can talk about whatever you want to. Okay? Too bad it's dark outside. In the summer, it would be light out, right? Hey, at least it's warm. Anybody have any questions?
How'd you have a question about?
Okay, yeah. Sure. Is it like one of the numbers on there? I could pull it back.
12.2.
12.2. Yeah, let me pull it up here. Okay, so this is the one where you've increased the moving mass to 100, leaving the radius and the number of washers the same. Predict whether the period will increase, decrease, or stay the same. Okay, that was the first part.
I just didn't know how to find the period without, like, the simulation on the period.
Okay, so let's. So here's what it means by use Newton's second law to do that. Okay. So we had this that. Seen? Yep. So the net force, I think I called this moving mass, times radial acceleration is equal to the tension. But the tension is also equal to the mass of the washer times g. So this is like the rotational part of it. You know, F is equal to ma. What is the actual force? Well, it's the tension. And then you know that the tension's got to be equal to the weight of the, do it back over here. This tension has got to be equal to the mass of the washers times g, right? Because that's not going anywhere. So we really have two different things going on. The washer, the weight of the washer is down, tension's up. But that's the same tension that is towards the center on the washer, or on the moving mass, I should say. Okay, so let's see what we can do with this. So I'm going to take this and write it down here just to give myself some more room. So moving mass times radial acceleration turns out to be equal to the weight of the washers. So moving mass, this acceleration is v squared over r. And then we also know that v is 2 pi r divided by the period. So I could take this for v and put it in here. So moving mass, v squared, so I got to square this whole thing, moving mass, v squared, so this would be 4 pi squared, r squared, over the period squared. This is v squared, this thing. And don't forget we still have a 1 over r. And then we got mass of the washer times g. what I'm trying to do, my motivation for doing this is to have an equation that involves t and all these different variables to see how they related to each other. Well, let me do one more. So one of these r's cancels out. So 4 pi squared moving mass times r over the period squared is mass of the washer times g. So now you can do whatever you want with this. Let me just put t by itself on one side. As long as I did the algebra correctly, I think it's okay though. 4 pi squared moving mass. That was an r squared and r, so we're left with 1 period squared. Okay, so let me put the period by itself on one side. So 4 pi squared moving mass r divided by mass of the washer times g, so moving that to this side, is equal to the period squared. So now based on just the moving mass, the radius, and the mass of the washer, then you can calculate the period. And then you could also predict what happens when you change different things. So if you make the radius bigger, the period's going to have to be bigger. So it actually goes around slower, just like planets orbiting the sun. All right, good. I'm glad you asked that. It gave me chills, actually. Okay, you're welcome. Circular motion is always really a trick.